Hello everyone, welcome to another class, another topic, and today we keep talking about how to automatically find vulnerabilities, and today by using fuzzing. So a hot topic, a hot research topic, a hot topic in industry, right? This is one of those topics, another one that I could give an entire course on that has so much things to talk about. The goal today is not to make you an expert in fuzzing, but once again to raise your awareness, to let you know that these kind of tools exist, and give you the opportunity to practice a little bit with this kind of tools for the first time for most of you, right? So in previous classes, we talked about static source code analyzers. That's basically the type of tool that scans the code without executing it. We mentioned about many benefits, like its speed, its easiness to run, and so on. But we mentioned also that this type of solution has some drawbacks, some limitations, some corner cases that it let go, and then you have to find other solutions to spot these corner cases. And one of those solutions that can detect the remaining points, the blind spots to static source code analyzers, is fuzzing. That's basically a dynamic solution. So right now, when you are using fuzzing, we are actually executing the application, searching for bugs in it. So let's try to understand how it works, right? So basically, you are going to follow the normal flow that you are used to all the classes in this semester, where you're going to give conceptual definition about fuzzing. We are going to talk about AFL as a representative tool, and then in the end, in the remarks, we have demonstrations. So let's talk about what is fuzzing. That, as I said, is a dynamic source code analyzing tool that actually you run the code and then you identify on the execution if there are vulnerabilities, if there are crashes, if there are any sorts of corner cases that you are looking for. So it's a complementary tool to static analysis. Ideally, you should like to execute both of them in parallel. And ideally, if you can put like static source code analyzers into your CI/CD pipeline, what you'd like to do here is that eventually, if you could put also a fuzzer in the CI/CD pipeline, so when you commit your code, the code is also fuzzed, the code is also dynamically analyzed, searching for bugs, vulnerabilities, and corner cases. And then basically, the core idea of fuzzer, it's very, very simple, because in the end, what we want to do is run the code and see if the code crashes at some point. And how are you going to make the code to go over multiple paths to know if any of the paths, any of the possibilities, any of the if or else's in the code might lead to a crash? Well, basically the idea is to brute force, as we saw previously for crypto and other techniques. But here the brute force is used for a good purpose. So what you are trying to do is not to actually hack into anyone, but basically to test the software to see if the software is vulnerable or not. Most cases for benign purpose, for fixing and patching. Some cases, the attackers also might do this to find the exploitable vulnerability. But most of the use case for fuzzing are benign, are the good guys, the white hat hackers that are trying to spot bugs. And the idea is we are going to give the application, the program under test, multiple inputs, varied inputs, and these inputs are going to exercise each one a different path. As you know, you have an application, one input takes the if, so it does not take the else. Other input is going to take the else, doesn't take the if. So if we have diverse enough inputs, each one of the inputs are going to cover a different path, a different execution flow into the application. Hopefully we cover everything. In practice, not everything, but most of the application. That's our goal. So basically, we are going to test all these possibilities to see if any of them works or not. And how we are going to generate these different inputs. And basically, it's a try and error process. So basically, we are going to get initial input that we call seed that works, that is know it's valid, and we start to mutate this seed. We start to transform this seed into some other input, and basically we do this over and over and over again, trying basically all combinations or many combinations. Ideally, in theory, once again, if we have infinite time, we can try all combinations and we could find everything. In practice, we have limited time, so it's a probabilistic approach. So we try a given number, and then we know that the application is secure, it's robust, according to that given number. So we know that if we have run the fuzzing for 1 hour, we know that, oh, this application is robust to the point that it can run for 1 hour without crashing. So the amount of inputs that you can generate for an hour are not enough to crash. Of course, if you run 2 hours, 3 hours, eventually big clusters run these things for weeks or even years, and well, that's another story, right? But in general, it's a probabilistic approach. So we are going to somehow brute force. The idea of fuzzing is in the end very, very simple. That is, we generate all these inputs, we randomly change the input, try all these random inputs into the application, and we see if the application accepts the input, process the input properly, and finish correctly, or if the application crashes. And when the application crashes, this crash might be simply an unhandled case. The application, for instance, divided a value by 0. That's not a security violation, but it's just a crash. Or it can be a security violation in the case that, well, what the fuzzer found is that, oh, we increased the input randomly, and then we found that after this time, the buffer is overwritten. So the fuzzer ends up finding out a buffer overflow, right? So this might happen. So we are going to try random inputs to see what the fuzzer is able to find. So that's the big picture of this class. This is the whole idea of fuzzer. So it's not something very complicated. It's something that you could do in theory by yourself. You could create a big for loop that generates all combinations of inputs possible, and then you pass these one after another to the application, and then you see via a try-catch, try-exception loop to see which ones are crashing, which ones are not. In theory, you could do that. The point is that here fuzzing is a type of tool that automates that for you. So basically, you don't need to write anything here. You just send your application to the fuzzer. The fuzzer is going to prepare the environment to you, is going to test it for you, is going to triage the crash tests, the crash inputs for you, and it's going to do this very efficiently, running everything in parallel. So instead of a sequential for loop, it's going to be done in multiple processes and multiple threads, speeding up the process significantly for you, right? But once again, the idea is pretty simple. Just throw a bunch of random inputs into the application for a long time, and then we're going to see if it crashes or not, right? So continuing here, it's important to classify things because classifying is in general the way that we understand the things. So it's important to know that there are different types of fuzzing strategies over there. As I said, this is a very complex topic. I could give an entire course. You could study books in each one of these subcategories because they are very rich topics. But just to let you know, basically to give you some food for thought and then clarify a little bit how things are, we have black box, white box, and gray box fuzzing. So these are the categories that we used. And of course, this varies how much you know, how much effort you put into the thing. So in the white box scenarios, for instance, is the best case. It's when you have like the source code available, you can instrument the source code, and then you have full control of the application. So this is generally what happens when developers are testing the application, because the developers have the source code of the applications. It's a white box approach, and then the fuzzer can put some inspection points on the application, and then everything is monitored and run, and then you can generate inputs that are more targeted because you know more or less what is the format of the input of the application. On the other hand, in the hardest side of the things are the black box fuzzing. That's basically when you have no access to the source code, you only have like a binary, and then you have to discover how it works. This is generally the case, for instance, of an attacker trying to exploit a known application. So the attacker is not the owner of the source code. All the attacker has is the binary code distributed by the creator. And then the attacker has to fuzz it anyway. It's still possible. You can generate the random inputs and try the application. The point is that since you don't know what is the format of the input, basically you have to do random guesses, right? So it takes more time, it's harder. When you do this white box, you know that, oh, the file format should be like this. So you triage invalid inputs by definition. When you do black box, basically you can't triage. What you have to do is to try everything. And in the middle between them, it's a gray box fuzzing. That's when you have a mix, like when you don't have the source code, but you have a definition for the file type, or when you have the source code, but the source code is only partial source code, not for the entire file, or something like that, somewhere in the middle, right? But in general, we are either, if you are the attackers, black box, or if you are the developers, white box. So here we are talking about the white box scenario. So everything that I'm going to talk about in this class, in the white box scenario, we are supposed that we are the developers, that you want to deploy secure software, and then you're going to create your software, your source code, you provide your source code to the fuzzer, and the fuzzer is going to do its job, mutating the inputs accordingly, right? So the fuzzer is going to follow a standard flow that, regardless of the type, consists on the input generation, that is this mutation of the input, and then input injection. That's basically you send this to the application, right? In real time, you input this to the application, and then you monitor the application to see how the application is going, if it's crashing or not. And when it crashes, you do the analysis step, that is, what is this crash? It's just a normal crash, a safety issue, or is it a vulnerability, a security issue, right? So all these aspects are important. There are research in everything. For instance, although this automated tool for the analysis step, humans are still required, because in the end, you need to disambiguate some cases to know, okay, is this pointer here a security pointer or just a safety pointer? Like, is this just a leak that takes to nowhere, or does this pointer contains a password and something more critical? So in the end, humans are still required at some point to disambiguate very, very complicated cases, although the fuzzer helps a lot, triages a lot of cases, but in the end, some type of human intervention is still required. And then, of course, there's a lot of research being done here, in general, using AI on how to automatically identify if a crash is a security crash or a safety crash. So lots of research on that if you are interested. And all the previous parts has significant research, and all of them are important. Even the basic ones that look very trivial, for instance, input generation, but they are not so trivial, and they are important, because if you are simply, as I said, naively brute force to try all combinations, you are going to create many invalid cases by definition, right? And the idea of fuzzing is that you have a good mutator to make it work, because you start from a known case, a case that works, a valid input, and then you mutate the input just a little bit, right? Basically, what we do is that we perturb a little bit this input, such that we can increase one value of the input by 1, or decreasing by 1, or replace one of the values by 0, and similar kind of things. And then, of course, we do all exponential combinations of all these mutations. Because what's the idea? The idea here is that most of the security problems, most of the vulnerabilities, the crashes, the bugs, the corner cases are going to appear exactly this, in the corner, in the boundary. So if you have like a condition, oh, A greater than B, and it should be, it's greater than equal. So the actual crash starts not when you are too far away from that decision boundary, but when you are really close. So if you get a valid input and then you perturb this valid input just a little bit, in general, this small perturbation, it's enough, to find off by 1 types of vulnerabilities. When you are a little bit off, when you forgot to check a very specific case, right? So in general, when we create input mutators, input generators, we want to create this type of mutators and generators that perturb a little bit the input, but not completely destroy and not completely random. That's the idea of fuzzer, right? So basically, if we do all this, we can put our fuzzer to work, and then we collect the pros and cons of fuzzer. The pros, I think, are pretty clear, because it's a very powerful approach, much better than the static ones, because in the static ones, you can much better in terms of its capability of recovering things, because statically you can still miss a few things. So in fuzzer, in theory, you cannot miss because you are actually executing, right? So you can find complex things, and well, you don't need so much ice, right? So fuzzer does many things automatically for you. It's pretty good for large code bases because you can simply run the application without taking a look at thousands of files. So there are many advantages. But there are many disadvantages, of course. The amount of resource that you put here, because you're talking about dynamic analysis. So you have to put like a virtual machine to run and then run these virtual machines for hours and hours to test your application, right? So basically this takes resources a lot, much more resources than static analysis, an order of magnitude more, right? So basically, this is the major con to fuzzer. And after these hours, remember, this is still a probabilistic thing. So there is no guarantee that you're going to find any bug, right? It's very probable that you're going to find because you are exercising all paths, but there is no guarantee, which means that you can still fuzzy an application for an entire week, and you are so unlucky that during this entire week, all the paths taken were like in the wrong direction, and there's a single one path that's clearly vulnerable, but the fuzzer never touched it by chance because it never mutated in that direction, right? This is still might happen, right? Because it's a probabilistic approach. You are randomly generating and randomly covering. So on average, these cases tend to not happen, but theoretically, there might still happen. So very, probabilistic solution, very powerful, that requires a lot of resources. So on average case, you put a lot of resources and you tend to find something interesting. But there is no guarantee that just because you put resources, you are going to find something, right? So once again, the proposal in the end is that hopefully this can be integrated in the CI/CD pipeline, but this once again makes the building process, the release process, is lower because right now when you commit, besides building, besides static analysis, now you also have to run some hours of fuzzing before you release the binary to ensure that, hey, I tested the binary at some extent, and then I know that at least there is no trivial bugs here. There might be more sophisticated things, depends on how much hours you put on it. But in any case, you are going to delay the release process by some hours because you are fuzzing before. So to make this happen in the real world, the development team has to buy the idea that, yeah, security is important. It's important to put some hours of our release time into the security testing via fuzzing, right? But basically, that's the idea. And then basically, what kind of bug you can find? And that's basically every type of bug, right? At least all the ones that we studied in this course. So impute validation, logical flaws, and memory corruption, including buffer overflows and other types of things, because we are going to need an input. The input is mutated, not only in its value, but also in its extent, or in the characters that you put in the buffer and all these things. So if you say the fuzzer, the input is a string, it's going to create strings of capital letters, lower letters, digits, alphanumerical, and multiple extents. And then it's going to keep trying, adding always like one more character, one more char, one more char, one more char to see until where it goes. And then eventually, if there is a buffer overflow, there is a chance that, well, the application is going to crash when you overflow the buffer. And well, then later you can exploit, right? Notice that this is not automatic exploitation. The fuzzer is not going to exploit the buffer overflow to you. The buffer is going to find where there is an overflowable buffer and is going to tell, well, after I put this number of bytes here, the application crashes. So it gives you the location that we call the crash site. And then what you have to do is to go there and then say, okay, I have a buffer overflow here. I'm going to write the exploit to here, right? The fuzzer doesn't write the exploit for you. The fuzzer just pointed the location because that's the location of the last crash the fuzzer had, right? That's the logic. If you are interested in automatic exploitation, automatically writing an exploit, this is exactly what state-of-the-art research in this field looks like right now. So integrating, for instance, AI, generative AI into a fuzzer, and then at the same time you fuzz, you find the crash site, and then the AI automatically writes the exploit for that buffer overflow in that location. So that's what we are trying to do in terms of research. But at this point, it's research development stage, not practical, while fuzzing itself, it's already there, it's consolidated as a standard, so it's practical, right? So that's what fuzzer can do, right? So let's talk about one of fuzzing tools. I chose to talk about AFL because this is the most popular one, right? As you can see here. But in this course, you are free to test everything, and basically you can use any fuzzer. There are many fuzzers out there, and you can use the fuzzers in your own project, right? Don't forget about that. So you have to do the project. Nothing impedes you to get your application, put your application under a fuzzer, leave it running some hours, and see if you get some crashes, something interesting coming out of it. You can use AFL or any other one for that. Here, I'm talking about AFL, right? So AFL, it's a smarter version of fuzzer, for instance. It does not randomly mutate the input or in a completely random way, but it uses a genetic algorithm. So there is some intelligence or some probability involved on how to do the mutations, right? So basically, there's this idea, once again, that the new generations of inputs should be somehow related to the previous one, to not completely modify them. So we perform some mutations on them. And it has an interesting mechanism to maximize coverage. Coverage is how much of the code you are literally covering, literally traversing, how much of the actual code you observe. For instance, when you have an if then else, there is natural a split between two cases. So if you only traverses the if case, your coverage is 50% of the code. If you traverse only the else, it's 50%. But if you traverse if then else, you have 100%. Each one of the if then else might have nested if then else's, right? So if you traverse only one of the case, if and if, well, you covered one out of four possible paths, so 25% coverage. So if you covered if then if, and in the other execution, if then else, well, you covered 50% because you didn't cover the else, if, else, else, and so on and so forth. So our applications can be seen as a big tree. And then what you're measuring with the coverage is how much paths on the tree we are covering. Ideally, we'd like to achieve 100%. It's very hard in practice, but if you achieve a higher value, it's probabilistically good enough, right? And that's what this fuzzer is trying to do. It's trying to generate inputs that maximize the coverage. So it's avoiding repetition. It's avoiding trying to go same way over and over again, based on the logic that, well, if I visited this path already and I didn't crash it before, there is no reason for keep going this way. The same is true is if I visited a place and it already crashed, because I know that, it's a buffer overflow. I already overflown the buffer with 10 bytes. If I put 11 bytes, I know I'm going to overflow again. So I'm going to waste the execution run to not get additional information. So it's better to exploit other places to see if I have a better thing. So AFL is not a pure fuzzer, but a smarter fuzzer, right? So this is a good candidate for inspection, and this is how a real-world solution looks like. So how to use AFL, we are going to cover this in the demonstration, but it's basically simple because AFL in the end is somehow a compiler. Since it's a white box fuzzer, what AFL does is that it instruments your code automatically for you. You give the source code, AFL GCC, as you can see, or AFL C++, AFL something, is going to compile your code, right, as you normally compile, but the AFL compilation is going to add some marks, some instructions some statements in the code. The same way when you were debugging before I teach you GDB, you were debugging probably putting some printfs and saying, hey, my code is here, I stopped it here, I'm about to execute this function. You were putting some prints to work as a markers, to work as a labels for the application. AFL is going to do the same. AFL is going to add some labels to your application to know if it's in the if it's in the else, if it's before and after the function, such that later AFL can read this information back and know how to guide the execution via one path or another. So it instruments the binary, and then later you execute the binary. When you call the step run AFL, that is AFL fuzz, basically what you're doing is saying, well, execute this multiple times, this instrumented application that you created and collect the information. You see that we pass the inputs minus I inputs. This is where you put the seeds, where you put the valid inputs. There will be mutated over and over again every time the application is called. So the usage is basically simple. You just have to install AFL or import AFL as a Docker, or the usual procedure that we are doing over this entire semester. And then AFL is going to run, and then you're going to see something like this when AFL is running and running for a while and trying to detect something. And then it's going to store in the results folder what are the crashes and other things that we have found, right? So basically, to close the idea, of course, I'm going to skip the minor details and go directly to the conclusions, because that's what matters. That is the idea of fuzzer. So remember, we have static analysis like static source code analyzers. We have dynamic analysis tools, approaches like fuzzing. Each ones have pros and cons. Ones are lightweight, like static analysis. Others are heavier, like fuzzer, requires virtual machines, and so on. But they complement each other. In the end, we'd like to have them in the CI/CD pipelines. Each one can automate a different type of task. So static analysis is the first thing that you should try, because it's easier, it's faster. The things that escape from static analysis, you run dynamic analysis in the fuzzer. The fuzzer, a naive fuzzer is going to use a brute force approach, try everything. A smarter fuzzer is going to have feedback information from the coverage, is going to mutate the input in a smarter way, perturbing it a little bit, such that you can maximize the coverage, you can explore more paths, you can try to find these corner cases. On average case, we find a lot of things, but remember, there is no guarantee that in the end it's a probabilistic, because we don't have infinite time. So the fuzzing quality depends on how many hours you are fuzzing, and the more you fuzzer, the more hours are required, the more resource you put. This in general translates to cost. So fuzzing is pretty good, but costs a little bit more. Security costs in the end, right? That's the idea. And once we have done this, we can go to some hands-on things, right? So let's try to